So in the first part of this second half of the webinar, we're going to extend what we've just learned about making queries over a data set, which make no side effect, to executing updates over the data set, which actually change what's there. What you just learned about construct queries, which is looking for a match and constructing a graph, is really the entry point into this when you're dealing at the triple level. So one type of update you might want to make is to query over the data, to form some new triples, and to store those triples in the triple store. Okay? The other kind of manipulation we might make is at the named graph level. So the reason every triple is assigned into a graph as like a container is we can do container level operations on that. So we can move them around, we can delete them, we can load them from an endpoint on a web. All of this also is standardized now in the Sparkle 1.1 update language. So just to recap, we can insert explicit data. We can add more data that we want to assert. We can delete things that have been asserted using the update language. Or we can delete and or insert things according to a pattern. So we can make a match first and then decide what we want to revoke or assert, we would say, what we want to remove or what we want to insert. So here's the very simplest thing to do to add some further data to the data set. Because we're being explicit about the data that we're adding, the keyword here is insert data. Okay? When we're dealing with updates of a data, it's very important to keep in mind this view of triples being contained within named graphs. Okay? So when we do an insert data, we can explicitly say we want to put it into a particular graph. So this is the graph that you might have just seen very quickly now and that you get to use in the exercises, which is a subset of music brains for the exercises that was loaded just before this webinar. Okay? If we want to add to that graph these triples that a music brains artist made to works, and furthermore that there's a title to one of them, Please Please Me, and a title for the other one, Something New, we can just express all of those patterns as triples within a graph to an update statement. And those will then be in the data set for anybody else's querying later. In the same way, if we want to delete data, we can do it explicitly by saying delete data and having these, we would say quads, where you name the graph and you have explicit triples. But what we can also do is the match that we described. So there we have a where, just like a where clause, just like in querying. So we have a pattern that uses variables, finds the bindings possible for those variables, for the data that's in the data set at the moment, and use those bindings to decide what we want to remove. So if we look at the where part, always the place to start in reading this kind of update, just like in reading a query, we'll see we have some ID for an artist from Music Brains, and they made some album that we want to have bound. Okay? And a condition on that is that same binding has to be the subject to a triple, again, in the current data set, that attaches a title with this property of Casualties. Now, Casualties was a bootleg album by the Beatles. So we might want to assert this in some places. We might not want to in others. So if we were in the position that we had asserted that there was an album Casualties, even without knowing what the resource ID was, we can bind the resource ID here, okay, according to the title, and we can also bind all of the triples where that album is the subject. So any further assertions about that album we can bind, and then just as we can say construct where to say what we want to return in a graph from a construct query is what we match, we can also say delete where. If we just said delete where, we get rid of all of this graph, okay? And as with the construct, if we put in a pattern, then we make that pattern from the bindings in order to pull it out. So we're pulling out all of these assertions about the album. So find the album that's attached to the Beatles, that's attached to this title, casualties, and revoke all of the statements about that album. If we execute that, that will change the data set so that later when we query about it, there'll be none of those assertions. Okay, so we can also combine where with insert, and we can do two things at the same time. We can have a where clause to look in the data set to see what we want to manipulate, and both do a delete and then an insert. Okay, so here, read the where part first. So we're looking for bindings where the current member, according to the DBpedia ontology of the Beatles, is bound to X, and that X is constrained that the name has to be Peter Best. Okay? Then we delete by using that binding to fill in this pattern. So we delete just that statement that the Beatles has current member X. Okay? This doesn't remove the second triple that we matched with this triple pattern. It doesn't stop that person's name being Peter Best. It just removes the relationship of them with the Beatles through the current member property. Okay? Then, having done the delete, we can do an insert using the same bindings for this pattern. Okay? So we found the bindings, we've used them to delete statements, and we're going to use them also to insert new statements. Here we're going to be careful to put them into a particular graph, okay? And then we're going to say that the Beatles is related to that bound X with the property former band member. Okay? So we can model revoking Peter Best being a current member and asserting that he's a former member, all in one operation here, all in one update. Okay, now, as I said, we can manipulate triples that way. We can explicitly put them in, explicitly pull them out, or we can use a pattern to determine which things we want to pull out and which things we want to put in. But we can also operate at the level of whole graphs, of whole named graphs. So we can create a named graph as a container, which, to give a small technical detail, may be a null operation. It may be that our particular store doesn't care about empty named graphs, so it might just ignore us. Okay? Implementations are free to do what they want with this statement. Load allows us to say, here's a document. We want the triples in that document to populate some graph in the store. So either we say, here it is locally on the storage, or here it is across the web with an HTTP URI. So grab the document and load it into a graph. Okay? Then we can clear a graph. So we say, we've got this name, this URI, for a graph that contains triples. We want to clear out all of the triples. Okay? Possibly differently, we have drop. So drop is clear them out and forget about the graph. But your implementation may choose to forget about the graph having cleared it. And then we have copy, move, and add operations that I'll talk about now. So just a couple of examples. We could create the graph for the exercises. Okay? Create a graph for music brains with a particular timestamp. We could load, this HTTP URI is for the specification of the FOF vocabulary. Now, if we just execute load and that URI, it puts all of the triples in the FOF vocabulary document into the default graph. And you might have caught earlier that I said putting explicit triples into the default graph is not necessarily a good idea. Rather, we want to put the triples into a named graph so that we know they're a unit, we can manipulate them, we can give them provenance information, we can say where they've come from because they're contained in a named graph. So better than just saying load and the FOF document URI, we could say load that URI into a named graph, and then we can manage that as a unit afterwards. One small caveat, because these are HTTP URIs, this operation can fail. If your network goes down, if the server that's hosting this goes down, this can fail. You're allowed to add a keyword silent to this operation to say, if it fails, just carry on. Okay? One good reason to know that you can do that is all of these updates that we're talking about can be chained. So you can have an update document with several individual updates, all with semicolons in between. If you have load in the middle of a bunch of manipulations and the load fails, your store might decide to stop executing your update request at that point. And if it's transactional, it might roll everything back. If you add the keyword silent, you give the key that says, OK, if this fails, ignore it. Just carry on and do the rest. Okay? And if everything else succeeds and your store's transactional, it might go ahead and execute everything and commit the transaction. OK, so examples of clear. Thankfully, you're not able to do this at the exercise endpoint. But if you set up your own Sesame endpoint, you can do things like clearing and dropping the graph. And you can do these copy operations. So we can say we've got one name graph, and we want to use it to populate another name graph. Okay? In this case of copy, you overwrite, in effect, anything that might have been in the destination graph. So you say scrap everything that's in here and populate it with a copy of all of the triples from the source one. Okay? Move is destructive of the source as well. So it says take everything out of the source, all of the triples out of the source, and write them over whatever was in the destination before. Okay? Add is non-destructive. It says get me all of these triples from the source and add them to the triples that are in the destination. So you still have, if that was already populated, the destination graph, you preserve those triples and you add more from the source graph together with them. Okay, now a short word about the protocol, how you go about, or how a tool on your behalf goes about issuing these queries and updates. We'll cover this in more detail in Chapter 5 when we talk about APIs. But just to give a basic flavor, a Sparkle query can be executed over HTTP, so all of this is HTTP-born. You can send a query either as a GET request, just like a browser does when you're retrieving a document, by URL encoding the query. So you get a long URL, you might have just seen in the example that I gave, with the query in the URL, and the response to that is some query results. You can also, with a query, do what's called a post, just like when you use a form on the web. Okay? Then your query document goes in an HTTP body, again, more details in Chapter 5, and you get back the response. An update, on the other hand, can only be done as a post. It can't be done as a GET, because a GET should not make side effects. Now, when you interact with an HTTP server this way, with a GET operation or a POST operation, you can often ask for what the encode. You can describe what the encoding of your request is, and you can ask for an encoding of the response. So when we execute a select query at the top, we can ask for the results, which is this table full of results, in the form of XML, in the form of JSON, or now in the form of comma-separated or tab-separated values. Okay? So the select can be quite amenable to whatever kind of environment you're operating in, whether it's heavyweight with XML parsing, whether it's browser-based with JSON parsing, or possibly for interaction with non-RDF systems, or just for viewing as a human with comma-separated or tab-separated values. The other queries, the describe and especially the construct, what you're returning is not a table, but a graph, which is described in RDF very easily. So you can ask for any of the RDF serializations. In particular, RDF in XML, the original standard for RDF, or Turtle. So you can ask for a Turtle description of the graph that you've constructed. Okay, one small example of what it means to get encode a query is here against DBpedia. And later during Euclid, we'll have some exercises where we ask you to use the hurl tool. That's the HTML version of curl that most people have on the command line, to see what that HTTP interaction looks like. But really, for the most part, you'll be using Sparkle tools like the endpoint for exercise 2 that wrap all of this up for you and just give you user interface. Okay, sorry, one last word on update. While I've said it should be done using HTTP post, endpoints are obliged to provide that at post, but HTTP itself extends a little bit and allows you to apply that as a new verb, patch. Okay? Again, we're really looking forward to Chapter 5 in terms of describing how RESTful APIs work and what patch actually means. Okay, so for the last part of the webinar today, I want to bring together two threads. We've looked so far at a lot of material on querying today. And what we introduced in Chapter 1 was the idea that when you encode your data in RDF, you don't just get a nice unifying graph model for your data. You also get the possibility to set up inference, to model either with a schema or an ontology, and say, under certain conditions, we can derive knowledge by reasoning. Okay? So the last part of this webinar is about what it means to have that kind of inference or reasoning behind your query endpoint, so how that interacts with Sparkle. The example that we've already been implicitly using and that we'll use more in the exercises is saying we have a big data set, which is music brains encoded in the music ontology. We have another data set, DBpedia, okay, scraped from Wikipedia. And there's an integration between them that's quite seamless when you allow reasoning behind your endpoint. So in particular, Music Brains has IDs for artists, as well as the IDs that we've kind of seen on the fly for tracks and for records. The artists themselves have Music Brains IDs with these long UUID-based identifiers. Now, through the examples you've seen so far, we've been dealing with the knowledge in Music Brains, things like which tracks are there on which albums, what's the duration of tracks, what are the members of bands. But we've been using DBpedia IDs from a completely different data set. And we're not in this ideal case where we share identifiers, where we just use one canonical ID for a resource like the one representing the Beatles. We actually have two different IDs and different vocabularies being used. But by setting up inference, we can, for example, say, what are the tracks on Beatles albums using DBpedia's idea of the Beatles. Okay? That's what we've been doing on the fly so far. And the basis for that particular use of reasoning is the ability to use OWL to say these things, although they're separate URIs, actually represent the same underlying thing. So really, they're equivalent resources. And anything you say about this one, for instance, they've released albums that have tracks on, and anything that you say about this one, for instance, they were founded in Liverpool, all of that gets merged together, whichever ID you use. So when we ask, who are the members, according to the music ontology that's getting populated by Music Brains, of the Beatles, identified using the DBpedia ID, and what is the genre, which is something populated in DBpedia, we can just put that stuff all together and execute this simple query and get back the merged results. Okay, so when we were poorer, when we only had Sparkle 1.0, there was no standard way to fit things like RDFS and OWL underneath our querying to know how that would work. What Sparkle 1.1 has introduced is what's called entailment regimes. So it says, in the presence of RDFS, in the presence of this flavor of OWL, if you've made these kind of schema statements together with your data, then this is what query results you should expect. So now we stray back into the RDFS part of the semantic web technology stack. And just as a brief detail, Rdfs Semantics, so what it means to have inference in RDFS, is documented, is standardized in a bunch of rules. So they say, under this condition, if you have a triple like this and a triple like this, then you can infer a triple like this. So reasoning's always of this form. Given triples of a certain form, you actually have more inferred triples. So as one example, the music ontology has this triple. It says that the member property that links bands with artists in that band has a domain, as we saw before in Chapter 1, of music group. So that means if any resource has a relationship with another resource in this member property, then the first one of those should be in the class music group. Okay? So if we ask over this data that just says Beatles has member Paul McCartney, Beatles has member John Lennon, Beatles has member Ringo Starr, and the same for George Harrison, okay? Nothing in that data says that the Beatles is a group, but because we have this schema, this ontology statement, if we ask the query, tell me all of the x's where x is in this class of music group, then we will get back, because of inference, if we have entailment, according to the Rdfs scheme, we get the result, the Beatles. Okay? So there's several possibilities for filling in the results like this, not based on what's been explicitly stored in the data set, but based on what can be inferred from the data set according to the schema or ontology. Another example, member, this same property, says the other side, the object to such relationships, must be in the class of agents. In fact, it doesn't say person because you can have, apparently, robots in bands who are non-person agents. Person's a subclass of agent. So we don't have that the range of member is person. We have that the range of member more generally is agent. And that means, again, with this data, where we haven't classified the resources for Paul, John, Ringo, and George, we can still make this query, tell me the x's, where x is an agent, and get back, by entailment, under the rule that applies to this kind of schema statement, the results that at least John, Paul, Ringo, and George are agents. Okay, perhaps more usefully, you may remember that RDF schema also lets us make assertions about properties, that one is a subproperty of another. So one is a more specific relationship than the other. So one example of this from the music ontology is the singer relationship that links a person to the band for whom they're a singer is a subrelation, is a more specific version of the performer relationship. Okay? So you can read it this way forward. It says, if you're a singer for a band, then you're a performer for the band. Okay? But not necessarily the other way around. Just because you're a performer doesn't mean you're a singer. Okay? But if we attach these relationships in the data, that John, Ringo, and George are performers and Paul is the singer, I don't think you do that globally because the others did sing sometimes. But if we had this data, and then we ask who are the performers, well, we've directly attached, we've asserted that John, Ringo, and George are performers. We haven't asserted that Paul is a performer, but we have asserted that he's a singer. It's not for the band, it's for the release. So Paul was a singer on Yesterday. From that, we infer that Paul was a performer on Yesterday. And when we ask for all of the performers on Yesterday, we get back, when we have that entailment, we get Paul as well as John, Ringo, and George. Subclass, slightly simpler idea of this inclusion. Instead of talking about the relatedness of two things, we talk about whether one resource belongs in a class or not. Okay? We can infer that something belongs in a class if we put it in the subclass, if we put it in a more specific class. So the music ontology says that music groups, okay, anything that's in the class of music group is also in the class music artist. So music group is a subclass of music artist. Again, if we assert that the Beatles are a music group, which we do, in fact, in Music Brains, everything is put into nothing is put into music artist directly. Everything is either put into music group or solo artist. Okay? But still, we can query what's in music artist, even though we haven't explicitly populated it, because of this entailment. So we go from the set that's got nothing in. When we add entailment, we infer that the Beatles are a music artist because they're a music group, and we return the Beatles. When we make schema statements like that, like music group, subclass, music artist, there are also some inferences that apply even without any instances to those classes, even without any resources that are related through those properties. So for instance, if we say music group is a subclass of music artist, we can infer that music group is a class and music artist is a class. Because if one thing is a subclass of another thing, there must both be classes. Okay? Even without any of our declared classes and properties, there are some things that hold as triples without anything else, without any instances, without any new classes, without any new properties. You can say things like, you will receive, as a result of certain queries, facts that always hold, like subclass, domain class, and subclass range class. Okay? It's actually from these things that we infer that in particular music group is a class and music artist is a class. But these two triples hold and are queryable when you have RDFS entailment, whether you have any classes or not. Okay? So it's always the case that subclass has a domain of class and a range of class. For that reason, those are called axiomatic triples. Okay? One reason to be aware of them is when you set up a store and query it, even before you've added any data, you can get back results for certain queries like these, things that just always hold. Okay, now one more thing to say about RDFS is there isn't any consistency checking. Okay? If it's derivable, it's returned from the query. Okay? And if you can say it in RDF, you can put it into the store. So for example, this property called member is worded slightly ambiguously. It's difficult to read A member B and know, does that mean that A is a member in B or that A has a member of B? Okay? So occasionally, we might write things that are not valid because we've misunderstood what this relationship means. So we might write that Paul McCartney is in the class of solo music artists, completely valid, and that Paul McCartney, we think we've written, is a member of the Beatles. Okay? But that's not the way around that member works. Member, as we said before, has a domain of the group and a range of the agent. So if we asserted that, with entailment and the music ontology, we would infer that Paul McCartney is a music group. And there's no contradiction there in RDFS. We said it, so it's true, and it's queryable. Okay? If we write a query that says, what is Paul McCartney, in which classes is Paul McCartney, we get back, explicitly, he's a solo music artist, and by inference, he's a music group. And there's no contradiction between those two things in RDFS, because we can't say, we don't have the power to say, he can't be in both of those classes at the same time. That is the kind of thing that we can say with OWL. Okay? OWL is a stronger language for building your vocabularies. Okay? We call those stronger things ontologies. But it means that the entailment is more complicated and more costly to query through. Some more things that we can't do with RDFS, for which we might want to use OWL features. We can't infer things, for instance, like if Paul McCartney made yesterday, therefore yesterday's creator was Paul McCartney. We can query that out, making an implicit inference, which we saw before with construct, but what we can't do is base our where pattern on such a thing. Okay? Because even though where applies to inferred triples just as much as asserted ones, it's not possible to produce that triple through inference from this one with RDFS. It doesn't have the power to swap these things around in the new property. Similarly, if we explicitly say Paul McCartney knows Ringo Starr, RDFS isn't powerful enough to say if X knows Y, then Y knows X through the same property. So we can't set it up to be queryable that Ringo Starr knows Paul McCartney in return. All of these things we can do with OWL. So we move on to OWL. And in particular, just like Sparkle had an original version and then an updated version, so did OWL. We call those OWL 1 and OWL 2. OWL 2 is quite friendly in that it says, you might not want to use all of this. It is very powerful. If you want to use a subset, there are well-defined subsets that are, how would you say, tuned, or that are well fit to different kinds of implementation of that endpoint that you're querying. So there's a profile called OWL2EL that does basic classification and that has very nice reasoning properties in terms of how long it will take. You've got one called QL, which is pretty much defined to be executable over a relational database. So if we just have a SQLable relational database, we can implement all of the inference that we'd like according to this profile of OWL, this combination of features from OWL called QL, we can implement over that. Okay? When it comes to having a native RDF store, so one that's built deliberately to store RDF and allow inference, we'd very often use a rule system to implement the inference. So we've got a profile of OWL2 called OWL2RL, which are those features that are the most direct to implement over the top of a rule engine. Okay? So very often, if you're dealing with a native RDF database, these are the features that you might want to pick from OWL2 to give yourself richer inference and the possibility of consistency checking on top of RDFS. Okay, so let's look at some of the things that you can do with OWL2RL. The first picks up the idea again of domain and range for properties that we had in RDFS and makes it more powerful. Okay? So the first one says, other than just generally saying that a property is a property, which means in the class of properties, we can say it's in a class called object property. That means we expect to have a non-literal resource as the object. So we're really looking for another resource with its own life that's involved in assertions. So for instance, we could say the property plays is an object property because we want its domain to be musician and its range to be instrument. That's a class that has resources in. Okay? On the other hand, has members or has number of members, we could say is the other type of property in OWL, which are kept apart from these, called data type properties. With a data type property, we expect, and to some degree can insist on through consistency, that the object will be a literal. Okay? And by attaching a range to a data type property, we can go further and say its data type should be, for instance, integer. Okay? So that it's in data type property means we expect the object in any use of this relationship to be a literal. By attaching the range, we say that literal should have a certain form. It should be an integer number. Okay, now, more things that we can do with OWL. When it comes to dealing with separate data sets, which might have separate, or at least overlapping, but to some degree separate vocabularies, we might want to do some alignment between classes and properties. So one example of this is we say we have the data set from DBpedia that's got some properties in the DBpedia ontology, like band member. And we have MusicBrainz that has a lot of data described through the music ontology. And it has a property called member. Okay? Taking those two data sets together and wanting to query over the top of them, we might want to say anything that's related through band member should also be related through music ontology member and vice versa. So we can use either of these two labels for what's essentially the same relationship. Okay? We assert that we have an abstract syntax in OWL, or underneath This is how we would write it in triple, the kind of things that we're used to writing and have been talking about throwing into RDF stores. Okay? So you could write this and say, band member is actually the same property as member in the music ontology. And with OWL entailment of a profile that includes this equivalent property bit of vocabulary, we can then query through either of these names for the relationship. For example, if we have Music Brains and it populates from Beatles, the member property to the 4 main Beatles, then we can write a query here that says what's related to the Beatles through the band member property. Again, not populated in the explicit data, but where we have this schema alignment, essentially, we can query through that other name for essentially the same relationship and get the 4 Beatles. You can also, in OWL, assert that 2 properties, for instance, length in DBpedia ontology and duration, which we saw before in the music ontology, are disjoint from one another. It means that 2 things that are related in one can't be related in another. And one reason we might want to do this is we said in music ontology, durations are measured in milliseconds. On DBpedia, lengths are measured in seconds. So you can't have the same length in seconds as you have duration in milliseconds. So if you ever have a track that seems to have the same value for both of these properties, something's wrong. Okay? We can assert that something must be wrong in that case by saying that these 2 properties are disjoint from one another. They can't relate the same things. Okay, now more about properties that we can do with OWL. We can assert any one of these 5 mathematical things: symmetry, transitivity, inverse between 2 properties, functionality and inverse functionality of a property. So to give some examples, symmetry says that if a property holds between some x and some y, then it must also hold the other way around. So it's what we were looking for before when we said, if Paul knows Ringo, then Ringo must know Paul. We could say that knows is a symmetric property, which both doesn't. Similarly, if we wanted to introduce a new relationship between music artists called associated musical artist, well, if Billy Preston is associated with the Beatles, then the Beatles is associated with Billy Preston. We don't want to have to assert both things. Instead, we say that the property itself is symmetric, and then if we assert one way, we infer the other way. So if we query for, if we query to start with without entailment for who's associated from the Beatles, we just get the Plastic Ono band in this top one. But if we say that it's symmetric, then all of these 3 things are related to one another. So as well as the Beatles being associated with themselves, they're also associated forward with the Plastic Ono band and forward by the inferred statement that turns this around with Billy Preston. Transitivity means if I'm related to one thing through this property that we say is transitive, and it's related to something else, then we can infer that I'm related to that thing through the property. Okay? So we might use this, for example, to introduce a subgenre relationship. So here's 4 musical genres: rock, punk rock, heavy metal, and black metal. If we just query for, without entailment, what is a subgenre of rock, the only result we would get are the 2 direct ones, heavy metal and punk rock. But if we assert the transitivity and query with entailment, we also infer that black metal, subgenre of heavy metal, subgenre of rock, therefore black metal is a subgenre of rock. And we get all 3 results underneath rock in the tree because of this transitivity. Inverse, where you've got 2 properties, and they're both talking about the same relationship, but in the opposite order. So for instance, if we say, okay, this is a simplifying example. If we say that member is its own inverse, strange example, then we would get everything that's associated in either direction with the member relationship. Apologize that that example is a little bit strange. A normal inverse relationship, we might say there's a relationship like parent of, so if X is a parent of Y, then we can infer the opposite relationship through an inverse like child of. Okay? So if someone is your parent, then you're their child. Okay? These two properties are the inverse of one another. A functional property says that for a given subject, so for one particular subject in this relationship, there can only be effectively one object. So the object is determined by the subject. So the music ontology has a property called primary instrument. And by definition of primary, one should only have one given, at least per performance, primary instrument. Okay? Now here's where consistency is a little bit strange in OWL. If you have two assertions about your primary instrument with two different URIs, that in itself is not inconsistent, because we have this ability to say two URIs can actually represent the same thing, even though they're syntactically different from one another. They're different URIs. So if we say primary instrument is a functional property and said Jimi Hendrix's primary instrument was electric guitar according to DBpedia, but Jimi Hendrix's primary instrument is also e-guitar according to DBpedia, the inference is that electric guitar and e-guitar must be the same. They must represent the same thing because they're both the primary instrument where you can only have one such primary instrument. Okay? Conversely, an inverse functional property says whatever the object is, it must only have one subject. So there are a lot of these in the music domain. In particular, properties that are used for identifiers. Okay? In linked data, we would like that everything's identified by a URI, but in the music world, there's many non-URI things that are used to identify particular resources. In particular, the recordings associated with tracks. Okay? So there are different schemes for giving IDs to those things. One such is this International Standard Recording Code, ISRC. Okay? So we can use a property which is inverse functional, or we could assert that that property is inverse functional, because music ontology doesn't at the moment. And then if we attach to a given recording this IRC, okay, and then we have a different URI, here a DBpedia URI, that's attached to the same identifier with this ISRC property, then we must infer that the subjects are the same as one another. Okay? So with a functional property, if you've got the same subject, the objects must be the same. With inverse functional, if you've got the same object, the subjects must be the same. Yeah? Two things with the same recording code must be the same recording. Okay, we can assert, this is actually the crux of what I was talking about earlier, the on-the-fly entailment that we've had. If we assert in the abstract syntax that two things are the same individual, the way that we write that in RDF is one is same as, according to the OWL vocabulary, the other. When we assert that, if we query using either of the IDs, we get all of the relationships, okay? Whether they were asserted in this ID or the other ID. This is how we can get things like what the music ontology says are the recorded albums or the tracks on them from something that we've asked, not a music brains ID, but a DBpedia ID, like McCartney, like the Beatles, okay? So because the Beatles is the same as a music brains ID, because McCartney is the same as a music brains ID, then all of the things asserted about those Music Brains IDs are equally true of the Beatles and of Paul McCartney, respectively. Okay? So just as we had the positive version and the negative version before, we have the same thing with this equality between individuals. We can also, in OWL, assert that two URIs can't represent the same thing. So we could say that the Beatles as a band is a different resource, is necessarily representing a different thing from Beatles TV series URI. Now, when it comes to linked data, when it comes to linked open data, there are very few of these different from assertions, but there are actually very many same as relationships. Okay? In the next chapter, in chapter 3, we'll talk about making alignments and producing same as relationships like this that link everything up much more, even without shared IDs, and that make querying much easier. Okay, now at the class level, I won't go in full detail of everything you can do with classes in OWL, a very rich language, but just give you some ideas. At the alignment level, we can say there are equivalent classes. So we could say, if we have from somewhere a class called musician, and we have, for instance, from music ontology, a class called music artist, we could say they're actually representing the same class. They're representing the same collection of resources. So if you put something into one, if you say that a resource is a musician, you infer that they're also a music artist. And if you ask for all the music artists, you'll include them, even though their membership of that class wasn't explicitly asserted. Okay? We can also have the converse of that. We can say two classes are disjoint. They can't share any members. So we could say that solo music artist from music ontology is disjoint with music group. Okay? Both of them are music artists, the superclass, but you're either one or the other. You're either a group or you're a solo artist. You can't be both. Now, just a few things that you can do with OWL to manipulate classes. In general, this is called class construction. It means given some classes, and maybe some properties, we can construct new classes from them, okay? Which, as an entailment regime for Sparkle, means we can query for membership of those classes. The simplest form of this is already inherited from Rdfs, and we've used, it's the subclass relationship. So where we say that music artist is a subclass of artist, sorry, that's not quite, no, that's not music ontology. Music ontology says, for instance, music group is a subclass of music artist. But whichever way around, if you put things into the subclass and query for the members of the superclass, you include those members. Okay? We can do more interesting things with classes. In general, class construction will make an anonymous class. That's a blank node, which is a class itself, and has RDF type or membership properties with our resources. So if we take, for instance, classes female and music artist, and we make an anonymous class, a blank node, which is a class that's the intersection of those two things, okay? If some resource is in the class female and it's in the class music artist, then it's necessarily a member of this anonymous class. Okay? Instead of intersection, we could have said union of. So if it's either in one or the other or both, then it's inferred to be a member of this anonymous class. Or if we use complement of, if it's not a member of the class that we specify, then it is a member of the anonymous class, and vice versa. When we form these anonymous classes by construction, we can give them names. And we've already seen the machinery to give them names. It's just equivalent class. Okay? So we can use a name like music artist and say the members of that named class are the same as the members of an anonymous class, which is this one that we form by construction, taking the union of solo music artist and music group. Okay? By asserting that, we've said more than that solo music artist and music groups are subclass of this thing. Okay? By saying they're both subclasses, if we put someone in solo music artist, then they're in music artist. If we put someone in music group, or if we put a group in music group, it's a member of music artist. Okay? But by asserting this, we've said the converse also holds, because it's an equivalence. So if we put someone in music artist, they must either be in solo music artist, or music group, or both. Okay? We don't necessarily know which. So when we query, the engine's not magic. It can't tell that something that you've only told it is a music artist. It can't tell whether it's either a solo music artist or whether it's a music group. But you can query to find out whether it's one or the other. And that will become true here. OK, so with 5 minutes to spare, let me just summarize what we've been through in the two halves of the webinar today. Perhaps the most important thing is to have covered queries according to the SPARQL language. Okay? We've said that there are 4 types of query. We have an ask query that, given a pattern, looks at a data set and says, can that pattern be matched? Okay? We talked about how we do that matching by forming a binding set and said the table for these bindings we can manipulate somewhat and give that table to the user who requested it. And that's called a select query. It's called select because just like a SQL select query on a relational database, you get back a table. Okay? And a lot of the modifiers to manipulate that table are in common with SQL. Group by, order by, things like this. Okay? The other 2 types of query, describe and construct, on the other hand, say your data set is a graph or a set of named graphs. Therefore, what you might want as a result of a query is a graph itself. Okay? So you can either ask for the description of some resources, either explicitly or by finding bindings for them with a pattern, and ask the engine to make a graph for you. Okay? It's called a describe query. Or you can say, I want you to construct a particular graph around the resources that you bind according to my specification. Okay? The easy way to do it is to say, however you match, that's the graph that I want. Okay? The more complicated form says, match it, make a binding set, and produce a different graph than that subgraph of the data set. Okay. In order to make those matches, we introduce query patterns. Okay? So what's called the basic graph pattern is a set of triple patterns, where instead of just asserting triples, as we've seen in Turtle, we say we want triples like this, but there are variables in. There are points that we don't know that we want filling in by binding. Okay? Then we saw beyond the basic graph patterns, you have keywords like union and optional that says, I don't necessarily want all of this pattern fulfilled. There's certain points where you could say either this, or give me this optionally if you have it. Okay? We covered filter, which says, you found these bindings, but some of them are not interesting to me. So I'll give you an expression to say which rows are interesting. And then we covered some modifiers. So we said, if there's repetition, you can remove it with distinct. You can say with reduced, try to get rid of some repetition, but it doesn't matter so much. We've said on the table, on the binding table, you can do orderings. Okay? You can put the rows in a certain order, and then you can do interesting things like just ask for a limited number of them according to that order, or offset according to the order, skip over some, and then perhaps limit. As part of the update language, we've talked about managing data within graphs using things like insert data to put triples in, delete data to pull triples out, or more interestingly, delete where. Delete where the data matches a certain pattern, or insert where. Assert new triples according to some pattern over the data that's already there, or the combination of two. Delete something and insert something according to a where pattern. And then we talked about managing data at the graph level. So for whole graphs in your data set, you can say, for instance, clear them out, or load them from somewhere else, or move one to another. We've touched briefly and promised to come back in a future chapter to the protocol, how you send these queries and updates to an endpoint. And finally, in this second part, we've talked about entailment regimes. We've said if you have a data set and you have a schema or ontology, you can ask for entailment that covers those RDFS or OWL features of your vocabulary, infer further triples than the ones that you've explicitly had in your data set, and query over both of them. Okay? So your query is fulfilled not just by the explicit data, but by data that can be inferred from it. And we've talked in particular about some of the RDFS features that are useful and some of the OWL features that are useful. Okay? The real take-home message, especially on OWL, is that gives you the basis for same as. That means if you have data sets with different identifiers, you can make those identifications between them, between Beatles according to DBpedia and Beatles according to MusicBrainz, and write a query that will merge everything that's known about the Beatles, everything that's known about Paul McCartney. Okay, in the next chapter, coming up in a future webinar, we'll talk about creating linked data that way. So how do you take sources like non-RDF databases, like spreadsheets, like free text? How do you take those kind of things and make linked data out of them? Okay? So one, how do you turn them into RDF? And two, how do you get that kind of interlinkage so you can query over different forms of data or data from different origins? Okay? We'll also talk about if you have two data sets, how can you decide what are the equivalencies between them? So can you go in post hoc and say, can we make these alignments in order to make querying over multiple data sets easier? And that's going to lead towards the music-motivated portal that we're building throughout these webinars. Okay, so exactly on quarter two, hopefully. I'd like to thank you for listening, hopefully to both parts of this webinar. If you have any comments, if you'd like to engage in general, please go to the Twitter channel, which is Euclid_project. And yeah, once again, thank you very much for listening.